I already see a number of people from around the world that I recognize. Welcome, everybody. Welcome. I see some folks from South America. I see some people from India. I see some people from the US and Texas. Not going to call anybody out by name. I see some friends from Germany. Oh, there's folks from Germany on the line. Welcome, welcome. I don't see anybody from Asia yet, but I know you're out there. So we are truly covering the waterfront. All right, so I think people will continue to trickle in, but considering we have a lot of material to cover, I will get going. Welcome. My name is Evan Hyde. I'm with coking.com, and this is our webinar for August, and we are here to discuss cutting and quench water quality and some of the things that we can do to overall improve its quality. As many of you know, coking.com, we're here to share knowledge and best practices and provide technical support and consulting and training directly to refiners and vendors and other people around the world. So if you have any trouble with your coker and you want some more site-specific support, please feel free to reach out to me directly, and we'll cover that at the end. And you all are obviously also familiar with RefCom. RefCom is the conference where we share this knowledge from ourselves and from many companies and vendors and refiners around the world. And many of you I know have attended our conferences around the world. So welcome back. And to all of you who are new, I hope you can attend a RefCom in the future. So a bit of housekeeping. As you all know, we are on Zoom. Since the pandemic, everybody knows how to use virtual meetings. Cardinal rule of virtual meetings is you stay on mute unless you are directly being addressed and talked to. Some of our friends are going to help manage that, but please try to use the mute button appropriately. And then questions. We are going to be inputting the questions in the meeting chat. Okay, so that's going to be the spot where you can input your questions, and feel free to put a question in at any time. I'm going to be addressing the questions after the presentation phase, but feel free to drop that question when it pops into your brain. And for those of you who are participating, if you would like to add your 2 cents to the conversation and address somebody else's chat question directly, feel free to do that. This is an open discussion, and I welcome everybody to be able to communicate with each other as much as it is an opportunity to communicate with me directly. So without further ado, let's get going. So too long didn't read summary at the top. Basically, there are a number of things that cause this erosion corrosion phenomenon. We're going to get into all these details later, but suffice to say, all the things that are on the left there is managing your coke fines to be ideally below 1,000 ppm. A relatively higher pH, slightly on the basic side, tends to help this erosion corrosion phenomenon. Managing your dissolved oxygen. For most of us, we have open top tanks, and the solution is basically saturated. So that also causes some problems. If you have certain types of stainless steel, that can be a problem. And generally speaking, you should not have any oil circulating around in this system. So with regard to how you manage this, again, there are some simple solutions which seem obvious, but not everybody does them, which is basically clean your maze, assuming you have a maze. I'm going to be addressing by and large, most of the people in the world that have, a standard pit pad maze tank design, but we'll address some of the outliers as well. But cleaning the maze every single shift will help a lot. Blowing down the water in your so-called clear water tank every single day will also help a lot. And then managing and monitoring the effectiveness of your procedures using infrared and particle size distribution testing will help you optimize that. Now, failing that, which doesn't work for everybody, there are other things that people have done, and there are some options presented on the screen. So here's a good example of what it can look like when the coke fines get out of control in your cutting water tank. If you look carefully, you'll notice this little thing right here, which is the suction strainer for the cutting water pump. And you'll notice that the coke fines are being maintained by that suction. So it's pretty evident that a lot of coke fines are ending up in the cutting water system, in the decoking valve, in all those components that we don't want them to be in, because we're not managing the amount of solids that are coming into this tank. So as a result, you can imagine all the bad things happening. So let's talk about this sort of quote unquote typical arrangement of a settling system. The most common one in the world is by far the maze, which is basically where we're trying to take an elongated flow path and shrink it into a smaller plot space by adding these overflow and these lanes arrangements, so the water comes in, moves around, and then gets transferred by a pump over to the tank. Right. So the typical effective length of all of the lanes is on this order of magnitude. Again, there are bigger and shorter ones. The depth also varies substantially around the world, but more or less the depth is somewhere on the order of 15 to 20 feet, in the order of 5 meters or so. There's typically a variety of overflow, underflow weirs, and the amount and position of the entry points we'll talk about later is highly variable. Generally speaking, at the far end of this maze, we do have some sort of either a long shafted pump or a submersible pump that lifts the fluid into the cutting water tank. One of the little interesting caveats, I thought, because we are often focused on safety with coking.com, is I wanted to mention that if you do have a long shafted pump, there is a limit to how long those shafts can be. And quite often, the geometry of this system means that that platform is actually lower than the walls. Here, we're showing it above the walls. There are many cases where it's actually below the walls, and that, in fact, becomes a confined space that needs to be managed as such. So a couple things. You'll see some overflow weirs right here, right there. And this is one of the underflow weirs right there. This is an interesting arrangement. You'll notice that there's a ramp in this first one, and that allows a front end loader to get into this first lane. Often we'll refer to these as lanes. So this would be lane number 1, lane number 2, 3, 4, and so on. So these guys actually have 5 lanes. These guys only have 3, right? So a variety of configurations out there in the world. So where does this damage typically manifest itself? Quite often we see a lot of erosion corrosion in the piping. And this is true of the high pressure and low pressure systems for not only the cutting, but also in and around the quenching system. We see challenges with the decoking valves, in particular immediately downstream of the decoking valve. We'll talk about that in a little bit. And if you have a lot of problems with your coke fines, it can manifest itself in terms of damaging to the internals of the cutting tool. So there's a nice picture of that right there. You see coke fines packed in there. Interesting, one time I remember I've actually seen it so bad where it looked like toothpaste was coming out of the nozzles on the cutting equipment when we got a particularly bad slug of coke fines through the system. So it's amazing how far things get. And I also chose this particular picture. This is the flow straightener from the inside of a cutting tool. Many of you would recognize. And there are pieces of shot coke in there. Now, it's debatable whether or not these pieces of shot coke arrived at the flow straightener because they were using the cutting tool as a jackhammer in the drum, or if it arrived via the water supply to the cutting tool directly. Both are equally possible, but typically we don't like to see, you wouldn't imagine that pieces of shot coke that big could make it through all the settling system, through the tank, etc. But coke is miraculously good at getting all over the place. We can have erosion of the cutting hoses, of the internal components of the rotary joints, etc., etc. I chose this picture. This is a photo of the drill stem showing outside pitting. And this can be a result of the water quality that is circulating around in your system, often caused by using a variety of sort of quote unquote unique sources of makeup water or potentially even sludge, getting yourself into this type of aggressive OD situation on your drill stem. But it can happen. And then last but not least, I will mention the quench water system also takes its suction from this tank. You get some erosion corrosion around the valves, especially. We've been really trying to drive to very low flow at the start of quenching to improve coke drum life and reliability. And this, as a result, is really stressing some of these quench water valves to be able to manage that very low flow and causing damage to the valves themselves and also the piping surrounding it. So keep in mind there and keep on the lookout via inspection. So what are we talking about here? Really what we're trying to do is we're trying to take a solid, which is nominally more dense than water, but the density difference is not huge, right? So the typical formula that we discuss when we're referring to this is Stokes' law, which is taking a look at the density difference between the particle and the fluid. There's a viscosity term in there. And this basically determines the velocity at which a particle will fall out of solution. And so we can measure and predict for a given size particle how fast it's going to fall in solution. However, as we already noted, that those mazes, they are there to allow water to travel horizontally across them. And so you're going to have a velocity profile of the water traveling across the maze, as well as a concentration gradient of particles in the solution as well. And that's further complicated by the fact that as you get closer to the bottom, so this is going to be the sort of the bottom of the settling zone, as the water is traversing across it, you're going to get traction and movement of that material. And as this layer builds up, so as the amount of fines in the settling system increases, obviously the velocity profile changes and the amount of material dragging across there, because you're still basically moving the same amount of drain water, the same amount of cut water across there. And as a result, you get increased velocity and increased traction across there. So there's some really interesting science out there that you can use to determine, the rate of, falling out of this. But, a lot of it comes from beach erosion and sand research. But if we take some of that math and we give ourselves a sort of hypothetical fines maze system, and all these units here are in meters. It's 3 lanes. Each of them is more or less the same length. The third one's a little shorter because of the sump. Depth is about 4 meters. So you see that, and you end up with a curve, sort of an exponential curve, which is settling velocity as a function of particle size. And for a given drain rate, so this is pretty healthy drain, almost 3,000 gallons a minute. Some of the bigger drums in the world with very large drain lines, they can actually exceed 4,000 gallons a minute drain velocities. Some smaller cokers with small drain lines, much, much lower. So all these numbers get factored into this set of equations, and you end up with sort of looking at, so as the fines build up in the lane, it's going to take up a certain percentage of that depth, right? So we start with 4 meters, and at 4 meters deep, with all these assumptions, you can expect that you're going to get everything bigger than 143 microns is going to fall out in that maze. Now, as the lanes fill up, let's say to 75% full, that cut point is going to increase to 286 microns. So these are the size of particles that we would expect to end up in the cutting water tank. So obviously it behooves you, as I said at the top, to continue to clean that maze very, very regularly, because it has a direct relationship to how much material ends up in your cutting water tank. So let's talk about what the cutting water tank looks like. Now, by and large, most of the cutting water tanks in the world that I've encountered look like this with a V-shaped bottom. Now, there are some exceptions out there. There's the inverted V, and then there's the single side slope. And for the most common, we would typically have some sort of drainage arrangement where the settling occurs in the tank, and we drain that back out. Here, the material sort of accumulates at the edges, and there's multiple drains around the side there. And then similarly with the single side, you could imagine a drain being at that one side. Now, here's a nice photo I dug up from some water quality testing that we were doing some years ago. And this is what it looks like after allowing that material that comes out of the tank to drain for 24 hours. So you see it's still a little bit cloudy even after 24 hours. And what this has to do is, again, very small particles take an exceptionally long time to drain. So what you're looking at in this curve is the blue line is basically allowing the dropout time for a single particle to drop 5 meters or for another particle to drop 10 meters. They're similar, but you'll notice that on the vertical axis, this is a logarithmic scale. So for a let's just say a 100 millimeter, 100 micron particle, we're looking at somewhere around 11 minutes to drop 5 meters, or if we look really hard, I think that's about 30 or 40 minutes to drop 10 meters. So there's a big time difference. And as you get to very small particles, so like less than 20 microns, so where would that be? 20 microns would be here. We're talking about settling times 5 meters in excess of 300 minutes, and potentially even as much as 1,000 minutes for 10 meters. So things take a long time to drop out. So what I think is really important to consider is when you make up the water into the cutting tank, and then when you choose to blow it down and by what amount, also plays a big determinant as to how effective the draining of these tanks really will be. And the last point, I know that many sites actually run their quench water pump all the time, and depending on where that ties back into the tank, sometimes that can have a continuous stirring effect to the tank, which prevents you from adequately settling out the coke fines that you otherwise would like to get out. So, and there's a lot of variation in the world. Definitely some things to think about there that as it pertains to your facility. So here's some particle size distribution analysis that was done for some water samples from a coker that we worked with. So I thought it would be interesting to say, okay, well, let's say I have a tank that is relatively tall and I want that particle to fall 10 meters, and I need to find quiet time because I want to get below 60 microns of particle sizes, right? So the coke cutting folks from, Rur Pumping, Flowserve, whoever, they're really interested in, they will say that most of the fines that do problems are bigger than 100 microns because they have momentum, they have the ability to do the erosion. However, there is some interesting data from some of our client sites that shows that very bad erosion can actually happen from, 20 or 30 micron particles. So it's not just the big particles that cause trouble. If it's an absolute concentration effect as it is a particle size effect. But let's say you wanted to get below 60 microns, you might say, well, I need 100 minutes of settling time. So I need to find a time when my tank can more or less be stagnant for 100 minutes to allow those particles to drop out, and then we will drain the tank and potentially, get to a relatively clear water situation. But you'll notice is that this is from actual quench water sampling. Let's see if we can find 60 here. 10, 20, 30, 40, 50. I think it's more or less here. Up we go. That cut is about 50%. So clearly they're having trouble because they're not settling 50% of the material that could otherwise have potentially dropped out of solution in a reasonable time, which is 100 minutes. 100 minutes is totally doable for 2 drum cokers. For 4 and 6 drum cokers, finding 100 minutes of quiet time in the tank is very difficult in many situations. So there's a variety of solutions out there about where to put the drain water, because the drain water actually drags fines into the maze, right? So there are some situations, I chose this picture because you'll notice that there's a drain in the pit pad area, but then also a separate one in the maze. Clearly they're using the one directly to the pad, but it has an entrainment function where it actually pulls some material into the maze. So the converse can actually be a problem too. You'll notice that for another site, they actually were using draining directly into the maze, but the maze couldn't keep up. So maze water was actually backing directly back into the pit during the drain. And also, you'll notice here, all the walls of the maze are covered up. That means that rather than the material flowing like this, it's just going straight across the top into the maze, which is also defeating the purpose of the maze. So managing the level and making sure the pumps are adequately designed, adequately sized to manage your drain rate is also important, because if you overflow this thing, it's not going to do anybody any good. So all of these things factor into how effective the maze will be. There's also a filtration effect from the coke bed itself, and this can be a good or a bad thing, depending on how many openings you have in your wall. So these particular folks, you'll notice that they had installed some metal grates in front of their maze with almost no openings. And this is basically because they had so much trouble with coke fines, and this is especially true with shot coke, so much trouble with coke kind of pouring through here and plugging out lane number 1, especially with coke particles, big ones even, that they just totally blocked it off. And then there's some other ones where they've installed some bars, and in front of the bars, you can quite often kind of stack, relatively big pieces of coke to provide some sort of filtration effect. And this works reasonably well, but it does stop water drainage out of the pit pad area, which can affect coke loadout, right? So there's a balance to be had here. And then you'll see this particular picture. The original layout was for fairly wide openings, but they installed some screens over the top, basically on our recommendation to minimize the coke entrainment into the maze. And there was some blinding of the screen. I think maybe going to a slightly larger screen, this is the best we could do on short notice. Going to a slightly larger screen, we usually say about like 1 to 1.5 inches, 1 inch to 1.5 inches openings is a good strategy here. But these giant openings are not going to stop anything. Big pieces of coke are going to come into the maze and really defeat the purpose of lane 1. So you kind of have to find a balance. This particular picture is an installation. I've only seen it once or twice in the world. I think it's kind of clever. They actually use coke as a filter, right? So what's not visible here is that the pit pad is over here, and the maze is over to the side. And as the water traverses inside this well, there's a basket full of coke, and that provides the filtration for the maze. And periodically, they actually lift this up, wash it out, get the small particles out, but put the big coke back. So it's sort of like a relatively inexpensive filter. But stuff still does get by, and you see floaters on the top of the cutting water tank. So I mentioned this on the top. It is important to clean the maze every day. I chose this picture because you'll notice again, the particles that are resting on the top of the water there look awfully big. So that means that this maze is probably nearly full of coke, right? And basically no longer functioning, and the water is just scooting across the top. It's not really doing anybody any good. So we do recommend daily maze cleaning. I do understand and feel compassion for the crane operators, because I know that cleaning the maze is often one of the most difficult things to do as a crane operator. So it's especially important to be done, but I know it takes time and is tricky. And if you're already time constrained because of unit capacity expansions, whatever, this can be a challenge. Now, it's also a challenge in sites that do double handling, which it turns out in crane sites is most of them. So there are some things you can do to consider, upgrading the crane or upgrading, some sort of operator efficiency. There's some decent benchmarking out there with regard to, how quickly, a well-trained crane operator can move coke, and compare yourself against that if you're really up against a time constraint. And then lastly, I want to bring up here that it's a good practice to, as part of your tracking of the unit, is to record how many buckets are removed during the maze cleaning, and from what lane, because this tells you what the carryover tendency is looking like. And this can be a function of a lot of things, coke quality, cutting technique, something else. But just by the sheer fact of recording it, it actually encourages the operators to do it on a regular basis. So, lots of benefits to be had there. So highly recommend that and use that as a sort of leading indicator of coke quality. So let's talk about if we're going to drain these coke fines out of the maze. There are a variety of designs that I've seen out there in terms of where this material actually goes. So if you see sort of the simplest design for a designer who doesn't really understand the complications of the system, they'll take your cutting water tank and they'll place it right next to the maze, and they'll say shortest distance between A and B is the green line. And unfortunately, as you can imagine, if you drain the tank, it's just going to go right back around in a circle. So that's not a good idea. Slightly better solution is the red line, which allows that drain water to sort of have to traverse the maze one more time. And that's better than green. But realistically, the best solution is actually to take that water, if possible, if you have the gravity and the system on your side, to take that water to the far side, and then it has to transit the whole system again and potentially give you the best chance for auto filtration of those fines out of the system once and for all. But I do understand that the blue line is a lot longer and it has a bigger risk of plugging, right? So you need to consider, how you're going to clean that line out, whether you're going to flush it after regular use. And then
depois eu vou pôr num potinho, pode deixar.
Lastly, there's a variety of ways to isolate these tanks. The most common design that I've seen is some sort of gate or butterfly valve, usually, a double block at the drain. But realistically, and I'll talk about this later, but there's some pretty good evidence that if you automate this system, which relatively few people have done, but I think it comes as a relatively inexpensive solution to try to manage this on a routine basis. If you automate this by adding an MOV and some sort of logic to when you do this, you can actually result in a relatively good drainage scheme. So let's talk about samples a little bit. I think I see some questions coming in, not a ton, but definitely some questions. So I want to make sure I leave time for questions. So we're going to keep on charging here. So as it pertains to the cutting water, we recommend ideally daily, but I'm a realist. I would like to see daily, but let's just go with weekly as a compromise with our friends in the lab. The sample system doesn't need to be over complex. This is more or less water. If you have other things in there that are potentially questionable, that's a different story. But if it's just water, you don't need some elaborate, DOPAC style sampling system. You just need a safe disposition for it and making sure that you allow it to run and become a good, clean sample is probably the simplest solution. Some sites have flowing loops, which is great, but in some of these cases, they actually have very long runs of tubing. And that complicates it because you actually have to let the sample run for a surprising amount of time before you can get a representative sample of what's in the pipe. So there's pros and cons of both, but making sure that you get a representative sample is important. So let's talk about, there's a lot of variation in the system because as we know, we do the batch process, which is draining, cutting, and making up of this entire circuit. So there's peaks and valleys in how the system behaves. So it's a good idea to sort of, if you really want to dig into this, to do some sampling frequency over some period of time, and do it maybe like every hour, and then do some additional sampling after key events. So I'd say after cleaning the maize because it stirs everything up, right? After draining, after cutting, so that you can really understand how this, the samples move as a function of time. And then you want to do this sampling a number of times because there's a lot of variation in this, day to day, shift to shift. To get a decent understanding of what's going on, you have to do this unfortunate, hour-long sampling strategy multiple times to get a really good fix on it. And then once you figure out where the problems are, you can set your sampling schedule based on where you think it might be the worst, so you understand the worst case scenario. And this is one of the things that we've encountered. It seems obvious, but I'm just going to say it. For a lot of sites that have some sort of laboratory automation system, there's a set time. 9 a.m. on Tuesday is when I take the sample. The label is going to be printed, but in reality, that may not necessarily be the right time to do that sample. Maybe it's 11 a.m. that day. Maybe it's 5 p.m. I don't know, whatever the cycle dictates, right? So it's fine to print the label, but it's really important that the operator actually take the sample at the right time and then record the time on the tag, and that needs to be input back into the LIMS system so that later on we can understand, well, when this sample was actually taken. And this is true for a lot of coker samples because of the batch process. You don't want to take a light coker gas oil sample in the middle of a backworm. It's not going to be pretty, right? So something to be considered. So this slide is basically here for reference. There's a number of sort of standard tests that we would recommend. Obviously, total suspended solids. We like it to be less than 1,000, as I said on the top. The best practice is realistically actually less than 500. Some people even do less than 200, if you can believe it. But I do know some sites that are struggling with 2, 3, 4, 5,000 ppm in their cutting water, and they have the reliability problems with the cutting system that come with poor water quality. Again, particle size distribution, we're looking for less than 100 micron ideally. We're going to talk about corrosion in a second, but pH and dissolved oxygen are critical variables to that mechanism. Now, there are a number of sites in the world that do other things in terms of making up their water. Some people do boiler feed water. Some people do fire water, which has questionable quality. Some people do strip sour water, which could potentially have phenols in it. And in some relatively rare cases, there are actually people that make up water with sour water, typically from the blowdown. And this has a result of, obviously complicating what you need to analyze for your particular facility. So there was a nice case study that was done by our friends in India back in 2008. It's published in Hydrocarbon Processing. You can look it up if you like. But long story short, basically, they were struggling with a high corrosion rate in their cutting and quench water, and they installed some corrosion coupons, and they were seeing 50 plus mils per year corrosion, and they did a number of things to manage that. And after managing it, they were able to get it down to 10 mils per year. And again, you can see all the details in their study, but principle, they put an oxygen scavenger in there because, again, dissolved oxygen contributes to this erosion corrosion phenomenon, and we're able to get the O2 down significantly lower, made some material improvements. They, again, like I alluded to earlier, they automated their drain scheme so that they are continuously and repeatedly blowing down the tank. And they've also added another corrosion inhibitor to sort of get this in check. So good case study out there. I'd encourage you to look at it if you're curious about this topic. So let's talk about pH. A lot of the chemistry that damages our components is a result of acid attack. So if you can do something to improve the pH to about 8 or so, you have a chance to sort of passivate some of those internal surfaces and sort of manage it from a acid attack situation. So that can either be done with chemicals, or your makeup choice of water could potentially impact your pH in that system. And lastly, temperature is a function. Corrosion is a function of temperature. As you would imagine, as the temperature gets hotter, corrosion gets more aggressive, and that is a complicated situation based on a lot of things to determine your temperature. But there are a number of sites out there in the world, and I think I may have seen some people on the call that actually have one of these heat exchangers. Generally not recommended to try to cool this system down with a heat exchanger because it's full of coke, right? And it's going to foul the heat exchanger. Now, I think it's possible, maybe with certain very fouling resistant designs or ones that are very easy to clean. It might be a manageable situation, but generally heat exchangers to cool this system down are not recommended. Now, in the literature, there's some discussion about microbial-induced corrosion, MIC. I've never personally encountered it. I've heard rumors of it being a problem in this circuit, but I've never seen it. And then under-deposit corrosion also is something that you'll read about in the NACE literature for this circuit as well. So let's think about where this erosion corrosion typically bites us. Oftentimes, I see it in particular in and around the decoking valve bypass. So what you're looking at is a photo from a Flowserve sort of Pacific style decoking valve. So this is the high pressure discharge this way, and then this is the bypass going back to the tank. And you'll notice there's some swedges here, and it goes from 4 inches up to I think 6 inches, very short distance. And each one of those swedges is an opportunity for eddies and turbulence, and you get pretty nasty corrosion in this particular area, and then also at the elbows. And so some other designers actually specify a longer straight run here. One of the things I like to see is potentially a removable spool. So people will actually cut flanges into this system and make it so that this little piece is prefabricated. You manage it with inspection, and if it gets a little bit thin, you just take it out and throw it away, and you put your new one in when the system's not running. It's an easy maintenance job, and that solves this particular problem. Now, so this can be true of this exact location for the decoking valve, but it's also true of other components, right? Generally speaking, it's been my experience that inspection and strategic repairs during downtime is more cost effective than upgrading the metallurgy. Now, I know sites that have gone to stainless or have gone to thicker material to manage this problem, but by and large, unless you have some exorbitantly bad coke fine problem, generally you can manage this with inspection. So some other sites, some other things on this slide, basically showing where some of the places are that can bite you. One of the other things I just mentioned is that in a given piece of pipe, it's quite often that we get accelerated corrosion on the bottom, 6 o'clock position, because when this system's not in use, the coke fines settle to the bottom. And then when you start it back up again, you get this inrush of velocity, which sort of cuts the bottom of the pipe. So with this sort of knowledge, I'd encourage all of us as coker specialists to help our friends in inspection define, what's your RBI strategy and your standard practice for defining your material inspection locations. Generally speaking, UT is effective, but there are sites and folks who will do spot check with X-ray to see if there's some sort of eddy related phenomenons there. One of the big things that one of the things I'm a big fan of is multi-stage water settling systems. If you were participated in our webinar from last month, you'll notice we talked about this closed Coke slurry system that was recently installed. And I reproduced this image because you'll notice that these are the two settling tanks for the water. This is the Coke dewatering. This is the water settling tanks. There's two of them, and they are huge in comparison to the Coke drums. So just get a sense of scale from these two tanks versus the Coke drums, and you'll see that to do this properly, you need a lot of tankage with a very big conical bottom. And after some growing pains and learning how to optimize the sequencer that controls this whole scheme, they've actually been able to dramatically improve the settling performance of this system to the point that some of their water quality coming off these tanks is some of the best in the world now. It wasn't on day one, but it is after much hard work and learnings from the folks at that site. So multi-stage watering, I think, is a great option if you have the real estate, right? So a lot of sites don't necessarily have that real estate, but putting a second cutting water tank in terms of all the other solutions that we're going to talk about in a minute is often one of the cheapest and easiest solutions to really get your Coke fines in check. There are folks that use chemical flocculants, and the chemistry is out there. There's some examples from our friends at Nowco and Champion X. These are the products they would use in this service. You have to do a detailed benefit to cost analysis because the products are relatively expensive. I think we're talking on the order of $1 million per year. So it just depends. But then also, you have to have a fairly complex, again, multi-stage settling system to where you can inject the chemical in some sort of smaller vessel, allow that material to go to a secondary settling vessel, and then potentially to a third one, which is the clarifier where the solids ultimately settle out, right? And then if you have that scheme, which there are some sites in the world that have like 5 and 6 tanks to do this, the water quality comes out great. So like what you're looking at here in the picture is right off the maze pumps. Water is pretty cloudy, and then what comes out of one of the other vessels is awfully clear. And this is after a retention time of, I think, on the order of 6 or 10 hours versus that 24-hour picture I showed you earlier, where even after 24 hours, you still have Coke fines in the water. So it's for sure flocculants work. It just depends on whether or not they make sense in your facility. Other systems that have been tried are hydrocyclones. So here we have an example of hydrocyclones that have actually been mounted up on the top of the cutting water tank. There are other solutions. I learned recently that Krebs, which has pretty much been the market leader in this for coker application for many years, was recently purchased by FLS Smith, which is kind of interesting. But they actually have a vessel where instead of they have all these little baby hydrocyclones inside the vessel. And that seems like a great idea. However, I'll come back to this in a minute. One of the things that's the biggest challenge with hydrocyclones is the water that comes in and it spins around and the clean water goes out the top and the dirty water goes out the bottom, right? So for the cyclone to function, there's this little nut in the bottom, and the opening of that aperture controls the cut point of that given cyclone. And unfortunately, that opening of that aperture is quite small, and it's just the right size for a little tiny piece of shot Coke, unfortunately. So if shot Coke ends up in this system, it plugs that little nozzle. And this particular installation, you'll see there's big cyclones and little cyclones. Obviously, the little cyclones have a better cut point, but there's an open bin where you can actually look to see if there's a stream of water coming out of each cyclone. And this is part of the operator rounds that are required for this system to function properly. And, it's pretty simple. There's a little isolation valve on there, and you take this apart and you clean that little cyclone. It takes 5 minutes. and it's back in business, but you have to be able to physically see that cyclone to make sure that it's performing its job perfectly. So hydrocyclones have generally gotten a bad rap, in my opinion, because they don't get the care and attention they need, which is, constant cleaning basically. Or if you have a totally enclosed system, you don't really know if the cyclones are functioning properly, right? So you have to do, a maintenance job to get in there to see if it's functioning properly. So generally work pretty well. And then there's other solutions. This is from a company called Tor. They are owned by, I just talked to them a while ago. Anyways, but they have a desanding technology, which I think is very clever. I haven't seen it in a cocoa application yet, but I'm generally curious to see if it'll work for us. They actually suck material out of the bottom of the tank and take it to a downstream position, but it actually uses it's sort of like a Dyson vacuum style, like vortex, like sucking to pull the material up and out. Kind of clever. If anybody's curious, we can talk more later about it. But if you do get yourself into a problem where fines are everywhere, you need to get them out, right? So the simplest solution is to lower the level in the tank and get up there with a fire monitor, blast the fire water around. And if it's not horrible, you can often slurry that material up, get it out of the tank drain, and it's pretty good. Another solution that I've used in the past, which has worked reasonably well, it's not perfect, is actually take a submersible pump. Here's an example from our friends at Toyo. And you actually put this on a crane and you take it and you lower it into the tank and kind of move it around and use it to pump the coke fines out. Now, you have to be very careful that you don't want to do this in such a way that you submerge it in the fines and then it will just get plugged up. So this particular one has a jet ring sort of on it that helps slurry the material around it, but also an agitator right at the impeller eye so that it actually kind of cuts through and slurries up any material that might be directly in front of the pump. So it is possible to do this. It works reasonably well. It is tricky. There are some other companies that sell or market some sort of kidney loop system, which takes a slipstream of that water, moves it around, cleans it up, and puts it back in the tank. I reached out to Debusk in advance of this presentation to get some of their details, relatively new to the market. I didn't hear back from them, but I do know that they're out there pushing this service. And our friends at the same people that make our heavy coker gas oil filters also have a water filtering solution that you might want to check into. And then there's dredging options for the maize. And then last but not least is, of course, you could just open the hatch and allow the coke fines out. During turnaround, this is often the way it's done. It makes a hell of a mess. Just make sure you have a really good containment plan. That brings us to the end of our presentation material. Longer than I thought. My apologies. But I will try to address some questions. Feel free to add any questions in there. So Matt asks, is a continuous blowdown, bottom slowdown of the so-called clear water tank? Yeah, I love that clear water. Continuous blowdown advisable rather than one time a day. So Matt, I would say probably no, because you're not going to get the velocity that you need to really blow that material down fast enough to get the material out that you want. So if you just have a trickle of water coming out of the bottom, it's different than allowing that material to settle and then kind of really draining it out hard and fast. So I'm more of in favor of a relatively short drain, but with fairly high velocity. The next question, Manjeet asks, what is the best for the clear water tank sparger and draining? I'm not so sure I understand the question. So maybe I think the spirit of it is there are a variety of sparger rings that I didn't talk about because it kind of touches a little bit into the proprietary nature of some of the various designs. But I think that generally speaking, If you do your tank drainage regularly and continue to be effective at that, sparging is actually not always necessary. Really, the sparger becomes handy is if you kind of let it get out of control, and you really have to slurry everything up. So the sparger helps then, but obviously when you sparge, you have to be strategic about it because you're going to sparge and basically fluff everything up out of the bottom of that tank. And then you need to kind of sparge it and then allow it to settle back down and then drain it out. So, using the sparger sparingly and also strategically is I think something to keep in mind, because I think you'll find that if you're sparging regularly, you're actually doing more problems by creating carryover than you really want. Okay. So Ron John asks, what is the best time to do clear water tank blowdown? So like I was trying to allude before in that discussion about settling time, you really want to try to find a time where you have a maximum amount of quiet time in that tank before you actually do the drain. So Ranjan, I don't know where you're from, and as to whether or not you have a 2 or 4 drum coker, but if you have a 2 drum, realistically, after the cut is done and most of the water has drained back into the tank, you should have some hours before the next quench and the next cutting is going to occur. So on 2 drums, you have hours and hours to figure this out. On a 4 drum with the overlap, you're really just hunting for a time in your cycle where you have probably more or less an hour with nothing happening on that tank. And there can be some little tricks you can do to kind of create that space in your overall schedule. But obviously that comes with compromises to the rest of the process, right? So Chandra asks, the saltation slope slop mentioned in the slide is incorrect. Oh, okay. The deposition of sludge will be gradually high with the flow direction as well as the wall restriction there. Okay. Be happy to talk to you later, Chandra, offline with regard to your experience there. Don't claim to know everything about saltation. I'm not a beach erosion expert. I've just used those models to help predict how the mazes are actually performing. And Chandra also asks, what will the flushing media be? I'm not so sure what flushing you're referring to. Chandra, if you want to clarify your question, maybe I'll have time to come back to it. You could maybe add like a reply to your question or just put it at the end of the stack. I'm not sure what you're referring to in terms of the flushing and the timing of the flushing they're referring to. And then Manjeet asks, due to the density difference between water and coke, should a iron, hold on, should we be provided with a iron floating fixed plate in the maze pit? Iron floating fixed plate. I don't understand what you're envisioning, Manjeet. I feeling that I don't know if you're talking about some sort of horizontally floating fixed plate or something like an incline plate. So there are so in wastewater treatment plants there are some movable plates that create some overflow situations, and I don't know that would necessarily create an improvement in this system, but I'd be curious to learn more about what you have in mind. I haven't ever encountered that, so I don't have a immediate idea on there. So Matt asks, oh, I got some more questions coming in. Good. We also have a few minutes left, but I'll keep it riding. Matt asks, is there a BS&W sample testing appropriate substitute for TSS? I think I'd have to go back and look at the standard testing methods for BSW versus TSS. I don't have them directly in my brain, but the total suspended sample test is awfully simple. They just take a known quantity of water, they put it across a filter in the lab, and they weigh how much comes out. It's about as easy as a lab test gets. So the BS&W also, I think, is a fairly easy lab specification, but the total suspended solids is awfully easy. So, I mean, I don't know. I would hope that the lab could do that for you. So Ryan asks, do you have a question? Do you have any experience with sieve bends or Molly self-cleaning strainers and water filtration system? Yeah, so Molly is also ProGuard, which is also Jonell now. They keep on changing names. But I do have some direct experience with testing that equipment in various plants around the world. And it works very effectively. They have like a 20 or 30 micron cut, and they have a 75 micron cut, so you can really optimize your cut point depending on how big a filter you want or how precise, how much fines removal you want to have. The challenge with these systems is that you have to design for the surge capacity. So like I was alluding to in your sampling protocol, you're going to find that there are times when a lot more fines come into the system than quote unquote steady state. And if these backflushing filters, if they get hit with a slug of fines for whatever reason, maybe you dip the maze on lane 3 and send an inrush of just a ton of coke fines into that system, it's going to get inundated very quickly. And it's going to get plugged up, and it's going to require maintenance because the backflushing will be ineffective. So to really do it right, you need a bank of these things. And creating a bank of them obviously is more expensive, and that becomes cost prohibitive. So that's really the kind of the balance that you're trying to play with any of the filtration solutions. So Maximiliano asks, is it possible to install an API separator with continuous removal of solids prior to the water tank so you can have the tank enter with less solids? Yes. So it's fairly rare, but there are facilities out there that use clarifiers with their cutting water system. They're huge tanks, and they have rotating mechanical arms that continuously remove those coke fines off the bottom, and they have very long residence times, very quiet water levels, and the small particles do come out. The challenge with those is, again, you just need massive clarifiers, and keeping the mechanical internals of the clarifiers running can be a reliability challenge. So some of the older sites that I know of that have these clarifiers, they're just big tanks now, because keeping the actual rotating arm working was quite a challenge for them from a cost effectiveness perspective. So I think Andrew, your question is very interesting about the percentage of fines versus total coke yields. I think that gets into a whole bigger discussion about quality of your feed and how you're running your unit, which is totally beyond the scope here, but it's a very interesting question. And I'll just address Claudio's question last. Maybe sorry, I missed Brian. So Brian's question is easy. Have you seen any devices traveling across the maze to prevent settling? And have you seen test devices for particles traveling across the maze or favor settling in the first lane? Microbubble wall? I don't think so. I've never seen anything like that. I'm open to all comers, but I've never seen anything like that. I mean, generally the overflow underflow scheme, if you manage your level in the maze properly, works pretty well. And then lastly, Claudio's question, what is the typical hydrocyclone efficiency? So a number of years ago, we worked a lot with this vendor, that skid I showed, called Triplan. And so I think if I remember correctly, the 4-inch hydrocyclones will do a 200 micron cut, and the 2-inch hydrocyclones, I think, will do a 50 or 75 micron cut, and that's a D50 cut. So they that just means they'll get 50% of those particles at that cut point. They do get some smaller ones, but they do let some bigger ones pass as well. So I hope I've done my best to answer everyone's questions today. I have a bit of housekeeping at the end. There's my email on screen. Happy to answer, some of your technical consulting questions directly. Feel free to reach out. If you have some questions about RefCom, reach out to my colleagues, Becky or Lindsay, at their emails. The next webinar, which will be on September 27th, will be focused on FCC. So you get a break from Coker Land. We're going to be talking about CAT spray systems from our friends at Spray Systems. They're going to be talking about optimizing spray nozzle and injector selection for FCC applications. And the presenter is going to be Chuck Monroe. So we want to thank Chuck for agreeing to present next month. And if you have something you want us to talk about, or you want to volunteer to talk about something, please feel free to reach out to us as well. We have a newsletter coming out soon. So I just want to thank everybody for participating from all around the world, staying up late, getting up early. We do appreciate it. And I hope this presentation was useful for you. So I will wrap it up and bid you all adieu. Have a nice day.